My friend and colleague, Dr. Benjamin Strauss, from an organization called Climate Central. I'll tell you about them in a moment. Ben grew up in Hastings-on-Hudson in Westchester County. He got his first degree at Yale in biology in 1994. He then went to the University of Washington in Seattle and got a master's in zoology in the year 2000. And then came back to the East Coast and did his PhD in ecology and evolution at Princeton, graduating in 2007. His first job and his present job was with a relatively new organization called Climate Central. Climate Central is a not-for-profit foundation that is based in Princeton, New Jersey, and it tries to bring science to the public, especially to do with climate issues. So they have a staff at Climate Central of about 20 staff with 5 or 6 PhD level scientists. Last spring, in April, the keynote speaker at our Earth Stock series was Heidi Cullen from Climate Central. So we're delighted that Ben has taken the time out of his busy schedule to be with us today. And I just want to read a little from a New York Times article that came out in March. It was called Rising Sea Levels Seen as Threat to Coastal United States. I'll just read a little bit. About 3.7 million Americans live within a few feet of high tide and risk being hit by more frequent coastal flooding in coming decades because of sea level rise caused by global warming, according to new research. The project on sea level rise, led by Dr. Strauss for the non-profit organization Climate Central. His work appears to be the most elaborate effort in decades to estimate the proportion of the national population at risk from rising sea. The papers he's published are scheduled to come out on Wednesday. That's the journal Environmental Research Letters. You saw that in my notice I sent you. The work is based on the 2010 population census and on improved estimates compiled by federal agencies of the land elevations, net coastlines, and tidal levels throughout the country. Please welcome Dr. Ben Strauss.
Thank you very much, Don. Now, shall I turn this one? Okay. Shall I turn this one off?
That's fine.
Because this one is on?
Yep.
Okay. Am I good? Can people hear me? Can people see me? Well, thank you very much for having me today. Thanks, Malcolm, for inviting me out. So I guess I have a talk in a few different parts. I'm going to start out by talking about the science we did. We published 2 papers in March. And then I'm going to talk about, I guess, the publicity around it and some of our we really were interested in doing both useful scientific research for itself, very strong, very rigorous, but also research that would help to engage a public audience in understanding this threat better. And so I'll talk a little bit about our thinking and our strategy and our approach to making sure that this was successful from a communications point of view, as well as from a scientific point of view. Alrighty, so here are the 2 papers that we published. The first was really about mapping low-lying coastal areas in the United States, quantifying the housing and population there. And the second was about putting a timeline on local risk from rising sea levels combined with storm surge. So starting on the first paper,
Maybe you better leave the room, I think.
Trying to kill the damn thing.
That's okay. It's part of modern living. So the first paper was really a glorified map. We had the good fortune of coming along at the time that some new data sets were becoming available. We used the National Elevation Dataset at about a 10 meter by 10 meter horizontal resolution. We kind of carved it out according to the NOAA medium resolution shoreline to help determine what's land, what's not. We use the National Wetlands Inventory to eliminate saltwater marsh from our consideration. We use the new tool from NOAA called VDatum, which is a pretty high resolution model of tidal levels around the US. So about 100-meter horizontal resolution, but just a few centimeters vertical error according to their testing and control points. And that just came online right before we published, so that was critical. And data from the 2010 census. Folks on the ocean side of things here will not be surprised to learn that the elevation of local high tide varies a lot across the United States. Partly that's because of variation in mean sea level, and partly that's because of variation in tidal amplitude. But much to our surprise, there have been no effort to do a national map of low-lying coastal land referenced to the high tide line in more than 2 decades. There were maps of land, low land relative to a standard sea level, standard elevation, but that, how much land is beneath, 1 meter above mean sea level doesn't really, it's not very meaningful if the high tide where you are is 2 meters above mean sea level. So this shows some of the variation in mean high water. And we analyzed, land and population relative to that local high water line. We called our adjusted elevation tidal, or kind of tidally adjusted elevation. And here you see by county populations less than 4 feet above the local high tide line, which is a pretty good number nationally in terms of being a level where the risk is influenced over the next few decades.
You're taking in entire county populations, not necessarily those affected by.
No. This is the population that is less than 4 feet above local high tide. Okay, so we can see that the biggest trouble spot is, unsurprisingly, South Florida, but also the Tampa area. There's a red patch in New Orleans. There's a bright red patch for New York City, but that's because the population is so high. It's a small fraction of the population under the level, but the density is so high, you have a large number. Also some in Southern California as well as the Bay Area. But another way to look at it, taking into account total population, is what's the percentage of a county's population under this level. And here the picture's a little different. It's much more dire in Louisiana, where there's low population density by and large, but a lot of it is less than 4 feet. In fact, much of it is less than below sea level. South Florida is still in trouble, and then you have some of the counties in North Carolina that just voted not to think about this in the red. Here's just a fun visualization of about 2,000 towns and cities that we analyzed. And this is part of the communications piece. We could have stopped with a kind of multicolored pixel scientific rainbow map like we're used to seeing in lots of papers, but we computed numbers separately for about 3,000 towns, cities, and counties, because that's where people live and that's what they'll be interested in learning about. In this image, the length of a line is, well, on a nonlinear scale, proportional to the total number of people who live less than 4 feet above high tide. And the shade of the line is, reflects the percentage. So dark blues are high percentage, light white is a low percentage. You can see New York City is a long white line sticking out, so it's a low percentage but a large number, whereas from Louisiana you see large absolute numbers and percentages, and Florida a mix. But this is fun because for data visualization, all this is the lines. There's no actual coast drawn. This is just 2,000 towns and cities. To boil that down, here's a look with an emphasis on Florida, top states and counties by population on land below 4 feet. There are, as you can see, the top 4 threatened Florida counties rival or exceed the risk in most states. Similarly, if you look at towns and cities where more than half of the population lives on land below 4 feet, the great majority are in Florida. And the top 20 cities, again, similar story. Just a few notes on methodology here. The numbers we published are simple numbers of population and housing below elevation lines. Simple bathtub elevation model. We didn't even take into account whether the land was connected to the ocean. You could have an isolated puddle right inland. Not including the Salton Sea and Dead Sea area of California. We kind of kept them out. But we did an analysis, and actually connectivity made almost no difference. And we did it both ways. And it was a difference of a percentage point of that. So we decided to be simple and make our results based strictly on elevation. We tried doing it at a 30 meter by 30 meter resolution, as well as our 10 by 10 meter, and that made almost no difference. And we did not do an error analysis because the underlying elevation data set comes from a really diverse patchwork of data, underlying data sources of different quality. But we did do some kind of thumbnail sketch analysis and thinking about this, and basically our analysis was over such large areas that independent errors in the elevation data would cancel themselves out, unless they're highly biased. So the second piece of second paper and piece of analysis we did had to do with building a timeline. So one thing is the map of when is this threat coming. And for that analysis, we started by making projections of local sea level rise, basically by dividing things into global and local components of sea level rise. We did an analysis of storm surge or storm tides. This is all at 55 NOAA water level stations around the United States. We did an analysis of storm tides using an extreme value analysis on detrended data to basically assess what's a 1-year storm, what's a 10-year, what's a century storm. We then combined those two to say, how does the picture of storm tides change as you increase the sea level? And then we finally built an integrated risk timeline that I'll explain as I get there. So as far as this global versus local sea level rise analysis is concerned, and this was the first effort to make local sea level rise projections for across the whole U.S. Part of our work was to start with a global projection, and we used 6 different emission scenarios, 19 different models to get a whole family of global temperature trajectories. We fed those into what's called a semi-empirical model of sea level rise, which takes global temperature as an input. This is the only model of sea level rise or projection of sea level rise which has been able to successfully hindcast sea level. So they can take data from parts of the last 1,000 years and successfully predict other parts. It's a statistical model that simply relates temperature to rate of sea level rise. It doesn't have any physical mechanisms built into it, but none of the physical models have been able to successfully reproduce observed sea level. So we used that for our global sea level projection. And then we also analyzed local trends. So for each of 55 gauges, we had a 50-year time series of sea level, basically subtract out the global component of sea level rise, and are left with a local component, we compared those local components to independent observations of vertical land motion from kind of continuously operating high accuracy GPS sensors, and where available, kind of long-term assessments on the scale of decades to millennia of vertical land motion. And it turns out that the variation in the local component of sea level rise over a 50-year time span can be almost completely explained by vertical land motion in our analysis. So other stuff is going on, but it's kind of decadal oscillations from shifts in temperature or ocean currents. But we felt for a longer term projection, it was fair to use these local components, assume that they're steady, and they're coming from very slow. They're coming from vertical land motion that acts that changes on a slow time scale. So safe to assume that it's constant over the next half century, with the exception of the West Gulf of Mexico, where a lot of it is driven, by subsurface fluid extraction, gas, oil, and water. So they're sinking a lot faster because they're pumping fluid out from underneath themselves. So just jumping back to the global model, here's the ensemble of temperature trajectories that we fed in to our projections. Here's a look at our local projections of sea level rise through the middle of the century. So you can see that there are hot spots in the Gulf and the Chesapeake in particular, and generally there's more sea level rise in the mid-Atlantic than the Pacific or the Florida Panhandle. The scale here is in meters. So pretty wide range, from some places 10 to 20 centimeters, other places up to half a meter by the middle of the century. So then we did our analysis of what is the storm surge, storm tide, flooding like at these locations currently? What's the historic baseline? We took 30 years of hourly data from the gauges, detrended them, looked for extreme values that were in the 99th plus percentile, fit parameters for generalized Pareto distribution, and then computed return levels and periods using those fit parameter values to come up with this map.
Excuse me, these are the annual extreme values?
Well, we started with, so I wasn't the captain on this part of it. I know we excluded, I'm not sure that we actually went year by year what was like the biggest extreme. I think we set a threshold that was 99%, and then took the top, all the events above that threshold, excluding events that were 2 consecutive days. So the extremes, we took, it was hourly data, but we took daily extremes. We excluded ones that were adjacent to each other, and that was the set that we used.
Okay.
So this is what we get in terms of storm tides. And this is integrating both surge and tide together. So this is based on observational data of how high the water got relative to the high tide line at these stations. And so the biggest storm tides are in the Gulf. An exception on the Potomac River, surely from runoff influenced flooding, and some much lower storm tides in Southern California, and parts of Florida that are either protected from hurricanes or where the bathymetry may kind of mitigate against a big storm surge setup. That's okay.
Maybe one underneath it.
What's GPD?
Generalized Pareto distribution. That's my colleague Claudia Tibaldi's bailiwick. She's the extreme statistics expert.
This is a very well-known technique for analyzing return periods of extreme data.
Yes, yes. No, it's a very standard method. And an interesting thing here is, you notice, I mean, the values are 10 times higher than the sea level rise projections from the middle of the century, right? We're at 1 to 5 meters instead of 10 to 50 centimeters. Then we put them together. And we've basically made the assumption that storms will have the same statistics in the future that they will have in the past. That's a baseline assumption. And that would imply that we simply offset return period curves by a fixed amount to account for the sea level. It's easier to explain here. Now, maybe I should have a pointer, or I can just walk up. This is even better. So in the green, you have a kind of contemporary return level, return period curve, showing the difference between a 1-year event, a kind of annual storm, almost half a meter here in Texas at Rockport, Aransas Bay, up to 1 3/4 meters as the 100-year event. There we go. Okay. And then we simply offset that. This is a simple vertical offset for the sea level, our best projection of sea level rise by 2030 and then by 2050. So those are the 3 lines of return, 3 different return level curves that we expect to evolve over time. So here we are. So here we are, just about 1.8 meters is the return level, is the current 100-year storm. But today's 100-year storm becomes about a 75-year event with, based on the sea level of 2030, and it becomes closer to a 50-year event by the time sea level rises by 2050, when sea level has risen further. So basically, today's 100-year storm becomes a 75-year storm, then a 50-year storm, and so forth. Now, here's a very different place. This is La Jolla, California. Much flatter curves. And a place we don't really think about storm surge or storms or flooding very much. Because they have, the 100-year storm is hardly different than the 1-year storm. They just don't get a lot of variation. And what's interesting about that is, here we are at 0.9 meters for a 100-year storm. Well, by 2030, that's happening every 2 years. By 2050, it's happening every day. So when you have these really gentle, flat return period curves, you have some surprises in store as the sea level rises. So we can do statistics like this. Today's 100-year event is a what-year event by 2050, and here's our best projections. By the way, all these are kind of integrating over the range of IPCC emissions scenarios, which are all below what we're actually doing from the last, from the 4th assessment report.
When you say we're doing, you mean society?
And that is, emissions are running higher.
CO2 emissions are.
That's right. This.
The higher than the worst case scenario they looked at.
Exactly. So here we have, by 2050, I showed you La Jolla, that's there. So today's 100-year event has become less than a 1-year event. Southern California in our analysis. Similarly, actually, in Georgia, where there were no hurricanes or big surge events in our baseline 30-year period. Interestingly, there's very little to no effect in most of the Gulf, because where you have big storm tides, and if you have a 10-foot or 15-foot storm tide as your 100-year event, what's a foot of sea level rise? It's not such a big deal. It doesn't change that risk a lot, but it changes the risk a lot in places that generally have very little surge. So the warmer colors, the reds and the golds, are Southern California and different parts along the Atlantic. And really, actually, pretty much the whole Pacific. So then we took this kind of information and we ran our models kind of year by year with the sea level rise projections, so that we could get down to a resolution of really estimating the risk of flooding to any arbitrary level by any arbitrary year. And we kind of rounded and smoothed things off to the decade level, because I mean, this is not a year-by-year projection exercise. It's really the overall trajectory we're on. But by combining local sea level rise projections and return level curves, we can get overall odds of flooding to different levels wherever we want. Here, in a kind of more public-facing graphic, we define extreme coastal floods as really the recent past's 100-year flood level. So we have an 83% chance of seeing that in Los Angeles by 2030. The 25% in the Florida Keys, the 23% in Boston. Those are the red lines. The blue lines, here's a close-up for the Northeast. The blue lines, we repeated the whole same analysis, subtracting out about 7 inches of sea level, because we said, well, what we basically subtracted out was the global component of sea level rise, the part that we can really assign to global warming. So we said, what are the odds of these high floods if there is no future sea level rise from warming, and there had been no past sea level rise from warming? In other words, how much has climate change and warming affected the odds of extreme flooding? And you see some pretty big differences between the blue and the red lines, I mean, doublings, triplings. That's how much climate change in the very near term, and even in the present, at most of our sites, climate change has already more than doubled the risk of what we call today a century flood.
So the blue lines are because of tectonic effects?
The blue lines, well, not exactly. The blue lines are just our calculation when you remove sea level rise from global warming. So they still do include any sea level change from tectonic effects, or the local component of sea level rise, so that it's a controlled comparison, more or less. And just looking closer to home, I want to advertise at the same time we published these papers, we published a web tool where you can type in your zip code, find it at searchingseas.org. You can have lists of statistics for different places in your extent. So here's a chunk of Long Island, where Long Beach is by far the most exposed place in our analysis.
Show people where that is.
Yeah, that I think is in here.
Keeps off the limit. Is it?
It may be right here. And here's a view around Manhattan. So here's Long Beach. And I happen to have clicked on Long Beach, so I get its statistics below 5 feet. And so we have this calculation of, there's an over 1 in 6 chance that sea level rise combined with storm surge and tides will overtop this 5 feet above the high tide line level by 2030 at the nearest flood risk indicator site, which here is the Battery, New York Harbor. So we have markers at each of the 55 points where we did analyses of storm surge and sea level rise. So users can move the water level, and the point is here, type in your zip code, go wherever you're interested in, and you can get a very local view, and you can also look at statistics of risk at the nearest indicator site. So local in place, local in time. And by integrating by thinking about storm surge together with sea level rise, we were able to kind of uncover these very near-term effects where a few inches really changes the risk of a big event. It takes a 100-year event and turns it into a 50 or a 20-year event. You can see effects in the short term. Most sea level rise work and communication in the past had been, well, in 100 years, that we'll see a meter of sea level rise, which, by the way, is less than a storm you might see every 10 years anyway. But by integrating them, we kind of brought the period of interest much closer to the present, which is critical for really public interest, policy interest. So some of our ongoing and future work is to do much finer scale local sea level rise projections, kind of interpolate basically between our 55 points. I think for sea level rise, that shouldn't be too hard. Much more ambitiously, to fully integrate sea level rise with the storm surge analysis. Instead of doing the simple elevation analysis that we did, where we said how much population, how much housing is below some elevation, say, well, okay, here are different sea levels of the future. Let's physically model the full storm surge on top of that sea level, like people do in some of the research groups here, and look at the risk of flooding throughout the landscape, following from that interaction between storm surge and sea level rise. Something else we're exploring and very interested in is to do sea level rise subtraction along the lines of what I've just been suggesting. If you accept that 5, 6, 7, 8 inches of sea level rise that we've already seen come from global warming. And we've done the budgeting, how much came from the ice sheets, how much came from thermal expansion of the oceans as the oceans warm. There's some dispute there, but I think it's pretty clear that the great majority, if not all, of the 8 inches we've seen since the late 19th century has come from those factors. Well, what does that mean? On a simplistic level, it means that every single coastal flood that happens today is 8 inches deeper, plus or minus, than it would have been without sea level rise. And what does that mean? It means more damage. The damage caused to structures by a flood goes up very steeply, non-linearly, with the depth of water. So every single coastal flood today has a larger footprint and causes more damage than it would have without global warming. And while the community struggles over, can we attribute this particular heat wave or fire, or there's a lot of passion over what we can call climate change, what we can't. In the meteorological world, right under our noses is almost trivially simple direct link between historic climate change and damages we're experiencing now for any single storm. Now, to really do it well, you'd want to successfully reproduce the footprint of a storm as observed using surge modeling, then lower the sea level by 8 inches, reproduce the footprint again, model the damages, take the difference, and the difference is your estimated bill from climate change, and you can go ring on the doorbell of homes that would not have been in the footprint except for these extra 8 inches and say, congratulations, like you were affected by climate change, end of story. Like no one can do that right now with any issue, and I think it's right under our noses here. We also kind of have the surging seas 2 and 3 in our sites. We're redoing our whole analysis with much higher accuracy elevation data, and we are.
Can I drop a bit?
Yeah.
Where are you getting this? Where are you getting this high resolution elevation data you just mentioned?
Yeah. So NOAA. Well, basically, there's something called LiDAR, which is LiDAR elevation data comes from laser measurements over planes, fly over the land, beam lasers down, and these data are being collected more and more around the United States. And it's now the case that over the next year, we're pretty much going to have a complete data set for the coastal U.S. And the National Oceanographic and Atmospheric Administration is orchestrating, is putting together digital elevation models for the coastal U.S. based on those data. So we're going to take that, redo our analysis, redo our maps, have new statistics, but also add in a lot more analysis. How many schools, how many road miles, how many wastewater treatment plants or EPA toxic sites or airports or you name it are within each of the different risk layers.
So how accurate is it, roughly?
I think the
I don't want to put you on the spot because it's
yeah, no, I think it's like on the order of 10 centimeters as opposed to a meter.
Probably better than that, yeah.
Yeah. So it's really good. So now I'm going to shift gears very quickly and then try and wrap up. But that was the more sciencey part of the talk, which actually I've given a lot less than this part of the talk, which is what happened in the communications. Now, when you do something and it leads to an editorial cartoon, you know that you've had some great success. And 47% of Americans don't think it's a problem. But I'm not going to write off that 47%. We have to reach that 47%.
Is that 47% of ever dependent on government? No?
Yeah, I don't know what the correlation is between the 47% that are takers and not makers. But I just looked at this again, and I couldn't believe that our numbers lined up so well, because this was published on March 23rd. As Malcolm noted, that we were fortunate to have front page coverage of the New York Times when we released this. I think it was a combination of a big headline about millions of Americans. It was a kind of a national assessment of risk from sea level rise, but also something where people could type in their own zip code and look at the places that they cared about. We were on all the national news networks and NPR and tons of stuff that led to a Senate hearing that I testified at. We did some quantitative analysis of the coverage. In 2011, there was on average 1.25 climate stories on the major network news per month, and we had 2 in a day, which is, mainly it's a sad indictment of how little the media is covering climate change. And similarly, we had a lot more attention in the major kind of print outlets than something like the National Climate Assessment, which was like all of the nation's best scientists getting together to say, here's the state of climate science every few years. That one, in the media, that's 2 articles. So you've got to think about audience if you're targeting an effort in communications, in science communications. For us, we were really looking at a broad public audience in our strategy. Getting in the Times helped with that. So, how do we do it? Certainly, getting in the Times was a critical piece that a lot of stuff leveraged from being on the front page. It wouldn't have been in the Times or the AP if it hadn't been based on really good peer-reviewed science. The journalists told me that directly. I just volunteered it. Being local, you type in your zip code and look at your block was key. local in place, local in time, as I described, a simple, easy online tool that was fast and easy to use. Being very visual, about 30% of the human brain by volume is for vision and visual processing. 10% or less, we think, is for language and logic. Think about how much money is spent on cosmetics, fashion, design, doing things to please ourselves visually. I think being very visual in science communication and climate communication is a really key element in success. Vivid metaphors, we came up with to try and explain the sea level rise and storm surge interaction. We came up with that basically it's like sea level rise is like raising the floor of a basketball court. You'll see a lot more dunks, right? It's raising the launch pad for storms. So a few more difficult things, I think, for a scientific temperament to do, but which I think are important in successful science communications. Lead with the headline, not with the caveats. In a lot of climate science, you hear scientists say, well, you know, we're very cautious, we're uncertain, and here are the complicating factors, and then in the second or third paragraph, you know, the world is about to end. You have to start with the headline, and then qualify it and unpack it and explain the complications. Also, think carefully about scientific conservatism. It's been shown that climate science models, more often than not, have been underestimating the impacts that we're observing as we're observing them. And I think climate scientists, and as scientists generally, we tend to take that even further, that when we speak, we tend to de-emphasize, tend to say numbers that are lower than we think, really. Which is conservative, right? We give an opinion that's kind of closer to where we are in the present, so it's less stepping out on a limb. And that's very appealing, it's safe, it's like it's at least this bad for sure. It might be worse, but I'm not being alarmist. I don't think alarmism is a good thing, but I do think if you think about it in the perspective of, say, a public safety officer, to say, well, it's less, it's low, is not conservative. It's actually radical and reckless, right? If you're a public safety officer, if you're in charge of policy and keeping people safe, you want to say, well, there's a 5% chance it could be this bad. I mean, that's what you're emphasizing, that's what you're planning for. And I think in the scientific community, we tend to, again and again, come at the opposite end of the spectrum. We call it conservative, but in a lot of contexts, it would more fairly be called reckless. But the benefit of it is that, preserving credibility is critical for any messenger. So it's a kind of tricky path to navigate, but there really is a counterpoint there that I think is often not appreciated by scientific communicators. Finally, your research will be misinterpreted. Corrected at every opportunity, but you have to be able to live with, to accept that it will be misinterpreted. Fight against it, but it's not a reason not to go forward. Do things in feet and inches, not just metric. We had to do a lot of extra computer time, so we put everything in feet and inches for the public side as opposed to the science papers. Forget why I'm showing that again. And just a lot of hard work. We built like 100 locally customized press releases and a mail merge program that kind of fed in statistics for that state and that town, and set that out to many hundreds of journalists, close to 1,000, and we really spoon-fed it. Like it was, and as a result, we had 800 stories, including like long independent reporting in small town newspapers, right? Your local journalist covering the article independently, not just a wire story, because we had the local information tailored for them on our website or in our press release. Make it personal and visual. She's standing in the projection of sea level rise for her lifetime. And yeah, I think. Let me just show you. So a next generation of surging seas, we're going to analyze a ton more things and divide it up not only by cities and counties, but by legislative districts, management agency districts, zip codes, producing the analysis that's digested in a way that connects to the places, the things that people care about, manage, want to talk about, not just a kind of multicolored scientific palette, but what does it mean for my district or my town or my zip code? So that's it. Thanks very much.
Thank you, Ben. We got time for questions.
When you were assessing the risk vulnerability of each particular station, did you take into account the criteria for a watch and warning from a coastal flooding advisory by the local WFO?
No.
No. So would it be that you could have, for instance, a 98th percentile surge event, but in reality that actually wouldn't be a flooding event given the watch and warning criteria?
Absolutely.
Right.
So you showed the flat return curves for La Jolla.
Yes.
So which shows that the return periods are decreasing very rapidly, right? And
It shows that the return periods
are decreasing changing very rapidly, right?
Yes.
Or they're expected to change
Yes.
very rapidly.
Yes.
So that in that case for La Jolla and other such places, this should already be evident in the data for the last 50 years.
Yes.
Is it?
I'm sure it is. We haven't done that analysis. My hope and suspicion is that waves are a big part of the equation for Southern California and much of the Pacific. And so those waves introduce a bit more variability, like storm surge does in the Gulf, so that if you were to incorporate waves, it would be a little less dramatic a transformation. But I don't know. But I think, yeah, absolutely. Like and NOAA has, I think they have published or will publish, basically, an analysis of how return periods have already been changing. I think it's, it's like I was saying in terms of the 8 inches. Floods today of a certain level.
So, but that is a situation where you can validate your projections directly. Right?
Yeah, that's true by saying like how has just choose 2 periods and ask how has the return interval changed.
Jeff?
So my question is based on a headline that we often see in Long Island. Thank goodness it was low tide and the effect of the storm was lower or reversed.
Yes.
So that raises a question of whether you have thought about taking into account differences of tidal patterns around the world, but particularly in North America, given that, this is a 2-part question, given that, for example, in the Gulf, tidal height is much, tidal range is much lower than it is, let's say, would be in a place like La Jolla. There are also other places where there's only 1 low tide a day, as we have in the Pacific Northwest, and then that is maybe coupled with when wind is running for a long time, and then a storm plus on top of it in the Gulf, you get a really horrible effect. So I'm wondering if you've taken those temporal and tidal differences into account.
We have implicitly, because the statistical analysis was based on observed water levels and their statistics. So those observed water levels were the product of whatever the tide was at the time, with whatever the surge was, whatever the wind was. Now, the whole exercise would have a lot more statistical power if we could separate out a distribution of storm surge with a distribution of tides, with, you know, possibly other distributions. And we would, I think, be able to infer a lot more from, you know, the same period of time. But at a first pass, we found this to be much more efficient, just everything
Right.
all
But
together.
I mean, it occurs to me that if you're looking for a mechanism for why the Gulf doesn't look especially different now in 50 years in the future, it's precisely that.
Yeah.
That what's explaining the Gulf is not the tide or anything like that, or even sea level rise. It's in fact wind patterns that are seasonal combined with when storms happen to be seasonally most frequent, which they might be positively correlated, for example.
Yeah.
There's a big difference between, in this part of the country, between hurricanes and winter nor'easters. With hurricanes, they say, you know, it's all to do with timing, you know, with respect to the tide. Whereas a winter nor'easter may last several days, in which case you guarantee you get several high tides in a row.
Yeah, a 3-day storm is but similarly, I'm thinking more thinking of these systematic regions like the west coast of Sweden and Denmark, where there's basically no tide.
Yeah.
Everything is due to wind patterns.
You know, another way of answering
That means sea level rise can't be as important.
You know, earlier I said that we assumed that in the future the statistics of storms will be the same. A more proper way to have said that is we assume that the statistics of storms and their interaction with tides and other forcing factors will be the same. That we really, by using just the observed water levels at the gauges, we're integrating everything except for sea level rise, because we had detrended the record by the sea level rise.
Let me
trend.
give you a very probably unrealistic hypothetical.
Yeah.
What if storms happen to be during the day in summertime in the Pacific Northwest? And that turns out you get low tide during the day. It means that would lower the probability of an effect. Not by a lot, but by enough to where a long-term trend would matter.
Yeah, and so if we could tease those things apart, we would have more statistical power in what we could do, but we did implicitly incorporate all of that.
Jay?
Leaving out the uncertainty that is caused by some of the faults in the data that you have, especially the topographic data that you're using, is a little bit, well, it's concerning and something you should watch out for, especially as you try to go down to the more specific and local level. And we've actually done that. We had 10-meter grid topographic resolution. 10 years ago we did that, and it was IPCC's first assessment. And when we took it to local officials in some of those communities that you were looking at, they pointed out immediately where all the errors were in terms of where the 10 or 50 year.
No,
that becomes, so if you're looking at a certain audience, I guess for the public in general.
The LiDAR, the next generation is going to be much better that
That's
way.
15 centimeters, so that's a foot. And you're dealing, plus or minus 15 centimeters for most LiDAR data. And if you're dealing with millimeter increases in sea level rise over these periods of time, I mean, it's something that you want to keep in mind as you do that, because we've already run into those issues.
The nice thing about the LiDAR is that the uncertainty is quantified. And it's not really, like the quantifications of uncertainty of error in the national elevation data set, like USGS gives them, but they're totally wrong.
I agree.
Yeah.
We have an expert on topography at the back here, Roger.
This is sort of follows up on Jay's question. What will you do, or what have you done when a property owner comes and says that you show their house being flooded by some event, and based on that, someone won't buy it, or denied insurance, or something like that? Are you willing to defend your use, or somehow interact with others?
Yeah, I mean, it hasn't happened yet, but we certainly talk with lawyers before we publish this and, disclaim it. I mean, it's educational, informational, free
Are you
speech.
willing to send a letter to an owner and say, even though this shows up on our map, it's for advisory purposes only, and so that they can then get some claim by a buyer or somehow a financial risk to that?
Yeah. Well, I mean that's an interesting question. We haven't come to that yet. I think if we had a request or an issue, we would. I mean, first of all, we'd stand by all the language that we've already developed. But if they wanted some kind of statement for us, we'd have to make a policy decision as to whether we would provide a statement, and if so, we would get legal help in so doing.
Brian?
I mean, just following up, I mean, the question is, how are you, or are you communicating uncertainty
Yeah.
in any of this graphically or to the public or whoever's using your web page? Without that metric of uncertainty, given everything we've discussed here, it becomes dangerous, I think,
Yeah.
In terms of interpreting that. I mean, I can appreciate the public perhaps not knowing how to digest some of that uncertainty. But, I mean, I know in the weather community, just being aware of worst case scenario, that's really on the tail of the distribution, for example, can be beneficial.
Yeah.
Even though it's very low probability.
Yeah.
It was kind of ironic to me, you were mentioning being conservative, or in the scientific community being conservative, but when I looked at your numbers, I almost thought they were conservative because you were
Yeah.
based it on a 30-year period of data, and if you validated that for Long Island, for example, where we've had the 38 Long Island Express hurricane, it almost seems like that would fall outside your envelope.
Yeah, no, it's fine that way.
And so it's communicating uncertainty as well as making sure the public or officials are aware of what could happen.
Yeah.
With that, and I didn't see much of that here, and I'm
Yeah.
worried that people would just take that one number of 1 in 30 years, every 30 years, and then run with it, and assume that my house is safe, for the next
Yeah.
29 years.
So great question. I mean, and we do qualitative. So there's a fair amount of qualitative uncertainty language behind information buttons and about buttons and things like that. We also present the timing in probabilistic terms. That is, there's an at least 1 in 6 chance of a flood to X level by decade D. So that, I mean, trying to suggest that there's some chance of something over an entire period. But, I take your point. It's a kind of thing we'd like to improve in the next round. Is kind of offering a wider range of different scenarios. I think it's still important up front to lead with simple images and numbers, but allow there to be layers behind that where people can explore different bounds. And there has been a move recently in just the mapping of land below elevation to include a kind of uncertainty zone or confidence levels. And in my assessment, all of those efforts assume perfect correlation of error in elevation, which I find to be a very unrealistic assumption. So, I think there's work to do there. If and when we take this, by the way, to the individual address level, which is something we're thinking of in post-LiDAR, we type in an address, not just the zip code. The readings for individual addresses, we would give a confidence range. Here's our best estimate, and we have a further estimate of the range of elevations where this might be based on our models, and certainly caveat that because it's getting so specific.
I find sort of thinking about human risk tolerance a very interesting subject. For example, if we were all sitting on an airplane today at Kent Airport on the tarmac, and the captain announced that there was 1% chance that in the next 12 months this plane is going to crash, I bet we'd all get out, right, before we took off. If you said the same thing about your house at the beach, you'd probably just laugh it off. So it's kind of interesting. We've got to finish now. Just can I ask a question? The next step of bringing this kind of communicating science to policymakers, the government policymakers, you had this huge burst of interest after the publication of your papers and the report. What next? I mean, you find that they are very conservative and they don't want to hear what you have to say?
Yeah. Well, there is a situation that, I mean, I think some local governments are very interested because they feel an existential threat, but I think others are not because they feel a different existential threat. That is, a lot of local governments are funded by property taxes, so property taxes come mainly from high-value real estate that's right on the water, and so they really don't want to have anything to do with publicizing in any way that there is an increasing risk.
Notice that Climate Central receives all its funding from foundations and not from government agencies.
Some from government agencies. Yeah.
Okay. Look, this is all very interesting. We better quit now. Ben will be here till 2 o'clock, so you're all welcome to lunch down the hall, and let's all thank him for this interesting presentation.
Thank you for having me.